Okay, so let me thank the organizers for, organizing this. This is the 1 decade is now, we are in 1 decade. So, great. So, what I'm going to briefly talk about is this very recent work that we did, which is about looking at bipartite particle number fluctuation in so-called dephased lattice system. So, I'll explain what exactly I mean by this. So, the work was primarily done by Lokesh, who is undergraduate student in IISc Pune, and the details you can actually find in this paper. So, motivation of this work was actually to try to understand certain universality in out of equilibrium many-body quantum system, and in particular looking at relaxations of observables, namely either local or non-local observables. But primarily, I'm going to talk about how non-local observables relax. And often it is said that non-local observables exhibit slower relaxation dynamics compared to the local observables, and their equilibration is described by few parameter hydrodynamic models. So what kind of, given a lattice, one of the very sort of a common non-local observable that one can actually think of is a bipartite number fluctuation. So you have a lattice of size L and you just choose any domain of your choice. So in this case, we are choosing a domain which is half of the lattice size. And you basically ask within this domain, I'm just going to look at the numbered fluctuation. So I have some lattice and I have some number of particles and I fix a domain and I look at what is the number fluctuation in that domain as a function of time. So, and you can ask obviously what is the motivation, I mean, or why one would be interested. There are different perspective. I mean, this is often connects to something called surface roughness dynamics. Number fluctuation also often gets connected to the so-called entanglement entropy and so on. So this is something which could be of interest to many people. So basically the central question is the following. So as I said, you have some lattice system and you have some initial filling and there are some interactions that are happening within lattice, and that lattice can be also say open. So it could be having some kind of dissipation mechanism. And within this setup, you have some initial state with, let's say, which starts with some zero number fluctuation. So basically you prepare the system in some number eigenstate, and then you ask what is the dynamics. So that's a central question. And often what you expect is actually a family Vizek kind of dynamical scaling. So note the sigma square is essentially the number fluctuation. And it often can we actually have a scaling form, a scaling of this kind, which essentially tells you that if you plot this number fluctuation as a function of time, the growth goes by this exponent beta, and which is the size independent of the size of the system. And after a certain time, there is this saturation time, which is denoted by T star, goes as system size raised to or domain size raised to Z, which is, you can call it a dynamical exponent, and then it also saturates, which depends on the system size. And if you take this and do a proper scaling, all these curves essentially collapse, and these exponents, alpha, beta, and Z, where alpha is essentially the saturation value exponent, they determines the universality class. So what alpha, beta, and Z is often goes by alpha by beta, determines the universality class. So of course, the people have looked at this number fluctuation in various type of systems. So very preliminary work was actually to look at isolated system, isolated clean free fermion system, where people observe that this number fluctuations show ballistic universality class with these exponents. And then there was recent attempts to actually try to understand if the system is not isolated, but if it's open, what happens? And turns out that this universality class changes. And the recent work in this direction had us put up some strong numerical evidence that the scaling actually have a diffusive, for short range lattice, they show that it has a diffusive exponent. So our motivation was actually to try to understand this setup more from an analytical aspect and also try to generalize the setup a little bit more. Also, there are, of course, this is not only a theoretical interest. I mean, there are a lot of experiments that are presently ongoing where people can also measure, literally like within a domain, the distribution of number of particles. And from that, you can calculate, or you can experimentally extract the number fluctuation. So these are also now recent fascinating experiments are ongoing in this direction. Okay, so what is our setup? So we kind of generalized it to a long-range lattice model, which is as from the point of view of lattice is still non-interacting, but having a power law decaying long-range hopping. And I make it open. So essentially, these are what we call the so-called dephasing probes. So this is the dissipator, so which conserves the number of particles in the system, but it dephases the coherences in the number basis, if you like. And then you essentially ask, what's the dynamics or number fluctuation? And of course, it can be written in terms of 2-point and 4-point correlation. So you essentially have to compute these quantities. Now what happens, one good thing happens about this model is that if you, the model is, the dynamics is very non-Gaussian because you have a quartic operator involved. But what happens is that if you look at 2-point or any n-point correlator, the equation of motion closes in n-point. So it doesn't generate hierarchies which are typically you expect in interacting system. So this is one good point, although Wick's theorem doesn't hold, but still n-point closes in n-point. That's one big advantage of this setup. But still with that, I mean, there's some difficulty. So what we do is we go to something called a strong dephasing limit. Meaning so this gamma is what we call the dephasing, meaning which is coming from the openness of the system. So you go to that strong dephasing limit. So that is the largest energy scale of your problem and your life simplifies a bit. So what happens in this strong dephasing limit is that you can write some effective equation for 2-point and 4-point, and that is all you need to calculate number fluctuation. So at the level of 2-point, if you do this strong dephasing, you can actually show for short range, it actually becomes like a diffusion equation on a lattice. And for if you have a long range, it just becomes a fractional diffusion equation with some effective diffusion constant given by 2j squared by gamma. So what we do is a simulation of starting with an alternate initial state, and you can actually see that the 2-point correlator or local observables relaxes very quickly. And when I say quickly, that means it actually relaxes independent of which does the relaxation rate doesn't depend on system size. So it actually relaxes pretty fast. And then you can do the same thing for 4-point correlators. The equation looks quite non-trivial. And also, at this point, it becomes both numerically and analytically very difficult to actually solve this thing because eventually this is, at this level, it's a L square cross L square. You have to deal with L square cross L square matrix size. And if you want to get this clear exponents, you have to really take large system size. So typically, the simulation at this level becomes slightly non-trivial. So what we found is that if you start with an initial state, which has translation invariance, just like, for example, alternate initial state of periodicity 1, there is something called a bond length representation, which you can go, where you can actually map this problem in terms of a single variable. So you can actually make it an order L by L problem, and now you can actually simulate large system size. And that's what we do. So essentially this 4-point correlator, which is a 2-variable problem, by exploiting this periodicity, you can map it to a single variable problem. And that actually helps you both extracting these exponents numerically as well as analytically. And that's essentially, yeah, so here I show that how the 4 points relaxes, and often they can relax actually in a much longer time scale, which depends on the system size. So just to give you the exponents, so this number fluctuation saturation, if you look at, the saturation rate depends on the system size, and this exponent has different values depending on what long range exponent value you take. So in fact, if you plot this dynamical exponent as a function of hopping parameter, you actually see that if mu greater than 1.5 or 3 by 2, you have a diffusive process going on. Otherwise, mu less than 1.5, you have a super diffusive. So for a long range case, there is a crossover in terms of dynamical exponent from super diffusive to diffusive. And you also start to see the emergence of this family Vsec scaling for number fluctuation in this system. And once again, you can now actually simulate quite large system size to clearly extract this exponent. So just to highlight again, if you have mu, which is long range hopping exponent less than 1.5, you have these are the set of exponents that you extract, which is super diffusive and diffusive depending on the values of mu. So with that, let me summarize. So this bipartite particle number fluctuation in open system also starts showing this, this scaling. For tight binding lattice, we also get all these exponents analytically. So if you're interested, please look at the archive version. And for long range case, you see a crossover from super diffusive to diffusive. So that's it. Thank you.
So if you have the dephasing, which is very fast, is there an equivalent Markov process description?
Yes.
What is it?
So essentially, if you take the strong dephasing, you can actually show that you can actually write a rate equation. So dp dt equal to wp, literally. And in that limit, the effective Hamiltonian actually become a Heisenberg, ferromagnetic Heisenberg model. So, and so essentially it's a Markov process at that level. And that's why life becomes quite simple in this limit, yeah.
So, you said you exploit translation variance,
Yes.
but originally you said one of your motivations was to work with open systems. Open systems,
yes.
But open systems will not have translation.
No, so it's a periodicity in the lattice.
Yeah, but they're not periodic, right? I mean, you're not working with a periodic boundary condition.
No, I'm working with periodic boundary.
But you said open system.
So when I say open system, meaning so in a sense, if you look at the geometry, so I'm having these dissipative channels or dephasing channels, but you can think of this as a ring. So I don't know.
So particles enter.
No. So it's not that kind of a. It's not like a bath attached with the two. No, it's not that. No.
Okay.
So I can model my openness in a various ways. So this is a very different.
So this
Open
is a different.
to environment. Huh? Open to environment.
It's open to environment. It's not like particle injecting at one end. No, so it's like this.
Yeah, in this class, this Z equal to 3/2 is also there, and that is very special in other cases called KPZ.
Yeah.
So for that correspond to some specific mu. Is there any significance of that mu?
No, I don't. From this model perspective, I don't really. So I have thought about it, but I don't really see anything special happening at 3/2, to be honest. So, but requires probably further exploration. But yeah, no. Yes, it is.
So why do non-local observables relax slowly compared to local?
Okay. Why do non-local observable relax? See, yeah, that's. Yeah, I don't have a very sort of
Okay, we can
precise
talk
reason.
about later.
Okay, so for typical initial condition, this is what happens, that non-local observable relaxes in a much longer time scale if you compare with local observables. But having said that, it's also very initial condition specific. For example, if you take a domain wall kind of initial condition, then you can even show that 1-point correlator also relaxes very slowly. So I'm saying that is also very initial condition. So typical initial condition, like if I compare at the level of such initial conditions where 1-point relaxes fast, 2-point relaxes slowly. But yeah, I don't really
so maybe
have
it's not a generic statement to call it like initial condition dependent.
So of course, the relaxation certainly depends on what initial condition you take. But I'm saying at least if you talk about alternate initial condition, the result I showed, here the 1-point relaxes in a time scale which is independent of system size. But non-local observable time scale, relaxation time scale depends on system size. So that's like a really, but what is the reason? Yeah, I don't have a very precise sort of.
Okay, thanks.
Reason,
Yeah.
Yeah, okay.
Yeah, let's thank our speaker.